Hello, Chem 112 students! This is Virginia here, and I'm going to go through the Decay for Days worksheet. This will give us a review of the types of radioactive decay that nuclei can undergo, and sort of the energy changes that are associated with those reactions. My email code is down there, and let me know if you have any questions. Let's go ahead and get into it. So our first topic is looking at the different types of decay. So we're going to go through these 5 decays, the first of which is alpha decay. And here they're asking us what's the reaction when uranium-238 undergoes an alpha decay. So I've started with uranium-238, and that number in the top left quarter is going to be the protons and the neutrons together, and this is what we call the mass number. So this is protons and neutrons. The number in the bottom left corner tells us just about the protons. So this is our atomic number, and that's what defines what atom we have, what element we're working with. And so they didn't give us the 92, but all you have to do is go to the periodic table, find uranium, and that'll give you the atomic number. Okay, so we're undergoing alpha decay, so we have to know what an alpha particle is. And so an alpha particle has a mass number of 4 and a charge of +2. So that tells me it has 2 protons and 2 neutrons, giving it that overall mass of 4. And sometimes instead of the Greek letter there, we'll write helium in. And that's the same thing, it's just reminding us that this is the same nucleus as a helium atom. Okay, so we're getting rid of that, and we're going to make something new. And for our new element, we want the mass numbers on the right, so here and for our new element, to be equal to our mass number on the left of 238. So I'm just going to do 238 minus 4, which gives me a new mass number of 234. And we'll do the same on the bottom. We need our number of protons to stay the same. And so we have 92 on the left. So far we have 2 accounted for on the right. So the atomic number for our new guy is going to be 90. And so to identify this element, we're going to go to the periodic table and look for what element is atomic number 90. And it ends up being TH. So that's going to be our balance reaction. And so they ask us, when is alpha decay actually used? And so alpha decay is our biggest type, it's the biggest particle, and so bigger elements that are trying to get rid of a lot of material to become more stable are going to undergo this. And so we're going to say if our atomic number, which is our number of protons, sometimes you'll see this referred to as Z, when it's greater than 83. So anything with more than 83 protons will undergo alpha decay. And we can see that our uranium had 92 protons, which is greater than 83. So next up, we have beta decay. And so we're going to start with carbon-14. And so I started with carbon-14, and then it has 6 protons, so I got the atomic number from the periodic table. It's going to give off a beta particle, which has no mass and a charge of -1. So our new compound, or our new nucleus, will have the same mass And now, in order for our number of protons to be consistent from left to right, this is going to have 7 protons, because 7 and minus 1 will come together to give us the 6 on the left. And then I look at the periodic table for what element is number 7, and that is nitrogen. So nitrogen would be our product of that decay. So how do we know if something's going to undergo beta decay? So in beta decay, we say this happens if we have too many neutrons. So too many neutrons, we want to convert one into a proton and keep our mass the same. And the way we can figure out if something has too many neutrons is just if the mass number is greater than what's on the periodic table for that element. Because if the mass number is too heavy, or is bigger than what's on the periodic table, that must mean it's too heavy, because the periodic table tells us about the most stable form of an element. So our third type of decay is electron capture. And it's just like what you expect. So we have calcium, 39. I know it has 20 protons from the periodic table. And I'm going to have it capture a massless electron. And to figure out what my new product is going to be, I'm just going to add the top on the left and the bottom on the left. So I'll have 39 still. And then my new number of protons is going to be 19. And then I can look at the periodic table and see that element 19 is potassium. Okay. So, we say that nuclei are susceptible to capturing electrons if they have too few neutrons. And we use a similar way to figure out whether we have too few neutrons, because if we're missing some, our mass will look too small. So our mass number is less than what's on the periodic table for that nucleus. Okay, and then next we have positron emission. I'm starting again with the calcium, and I'm going to give up a positron, which is kind of like the opposite of an electron. It has a +1 charge, but it has no mass. And then I can figure out what my product is by keeping the masses and the number of protons the same on both sides. So I'll still have a mass of 39. But now my number of protons for my new element is going to be 19. So 19 plus 1 will give me the 20 over here. And this new element is, again, potassium. So you might have realized that electron capture and positron emission gave us the same end product. We have the same result. Okay. And so it's going to be useful in the same case where we have too few neutrons. So our mass number is going to be less than our periodic table mass. And so you might be a little confused because we have two decays that give us the same product. And so I just want to point out that electron capture tends to happen to atoms that are deficient in neutrons, which is the same for positron emission, but amongst that subsection, these ones tend to be the heavier ones. So you can kind of think of it as the big ones need a little help being, an electron coming and smacking into them to reach their more stable form, whereas smaller nuclei, it's easier to go through that process without having that outside influence of the electron coming in. Okay, and so finally we have gamma decay. And so all gamma decay really is energy. So as you all know from nuclear reactors and power plants and unfortunately nuclear bombs, that these processes have a lot of energy associated with them. And so that's what we keep track of and call the gamma decay. It's just energy. So here on this next slide, we're going to start predicting for different elements what type of decay they're going to undergo, and then write the reaction for that decay. And so our first example is oxygen 14. So I just looked at the periodic table and found what its atomic number is, which is 8. So it has 8 protons, meaning that it must have 6 neutrons. And to figure out what kind of decay this is, I'm going to look at the mass from the periodic table. So the periodic table mass for oxygen is about 16 AMU. Okay. And so our mass number here of 14 is smaller than that. And so if it's smaller than that, that tells me we have too few neutrons. And if we have too few neutrons, we're going to undergo positron emission. Okay. And so then we can predict what our new product will be. So our mass number will stay the same, but now our atomic number is going to go down to 7, which here is going to be nitrogen. Okay. And we can kind of check if this makes sense by looking at what the mass for nitrogen is on the periodic table. And the mass for nitrogen is about 14 AMU, and that's the mass number we found for it here. So it does seem like we're going and making something stable at the end of this reaction. Okay, so now we can look at radon. And what I'm noticing here is that radon has an atomic number of 86. And so 86 is greater than the 83 atomic number. And so that tells me we're going to undergo alpha decay. So we can go ahead and say we're going to lose an alpha particle. So our mass number is going to go down by 4. And our atomic number is going to go down by 2. And then I look on the periodic table to find what has an atomic number of 84, and it's this polonium. Okay, and then for the last example, you can see that our atomic number is again greater than 83. So same setup from there. And so we'll again do alpha decay. So we'll lose our alpha particle. So our mass number will go down by 4. So it'll become 100. And our atomic number will go down by 2. 96. And we can look at the periodic table to figure out which element is 96. And that is this Cm. Okay, so for predicting, what I like to do is look at the atomic number and see if it's greater than 83. If it is greater, alpha decay. And if it's not greater, then we have to use the mass number. And I see, how does my mass compare to what's on the periodic table? If it's smaller, then it's going to undergo positron emission. If it's greater, it's going to undergo beta decay. So sometimes one decay isn't enough to get us to a stable product. Like we decay a little bit, we make something else that's radioactive, have to do it again, and there's a few steps before we reach something that's stable. And we can predict what that's going to be if we know how many types of decay we have to undergo. So here it says uranium-238 is going to undergo 10 rounds of alpha decay and 7 rounds of beta decay, and we have to figure out what it'll end up being then. So I'm going to do 10 rounds of alpha decay and 7 rounds of beta decay. And I'm going to make something new. So right now I'm just going to call it X. So it's going to be the same logic that we used up there. We need our mass number to be the same on the left as it adds up to be on the right. We need our atomic number to be the same on the left as it adds up to be on the right. So for the alpha decay, we're going to lose a total mass number of 40 when we take the 10 into account. And we're going to lose 20 protons. From the beta decay, our mass, we're not doing anything to the mass. Okay, but we are giving off 7 negative charges. And so we need these to add up to be the same on the right as on the left. So we can set this equal to 92 and 238. And figure out what our mass number and our atomic numbers are going to be. Okay, so the mass number on X, when we do the math to get rid of those 40, it's going to be 198. And the atomic number is going to end up being 79. But as it's written now, that's not going to be an answer choice on the exam, right? We want to figure out what element that is and get rid of our, big X placeholder. So we look at the periodic table to find element 79. It's a pretty good one. Oops. It ends up being gold. And you can see we ended up with something that has an atomic number less than 83. So that kind of shows us that it's done with its alpha decay process. And gold has a periodic table mass of 197. So we're pretty close in terms of mass also. So we've made something fairly stable. So now that we've talked about the way in which nuclei can decay and become something new, we want to think about how quickly that can happen. And what's neat about nuclear decay is they always follow first order kinetics. Always, always, always first order. And you all already know how to do first order kinetics. You've got it. So it's just going to be recycling some of that knowledge you already have. And so we know for first order, that's the equation where we have the ln. What we do in nuclear is, instead of saying we have some compound, we just say, oh, I have some nucleus. So N. So we'll have how much of that nucleus we have at some time equal to the ln of that initial value minus KT. And you'll see here the equation that's already on the sheet. They've just done some rearranging. And we'll have the same T1/2 equation for first order. 0.693 over K. And there's a version of this equation on the data sheet where you have this part, but then also, where it's combined with the half-life equation. And it kind of gives you a way to forego K if you don't want to deal with that K value. Okay, so this whole thing is on the data sheet. And one thing I do want to say about the kinetics of these nuclear processes is we can't do anything to change how quickly they proceed. You know, if we take our bottle of uranium and put it in the freezer, it'll still just decay as quickly as it did when it was out in the sun. There's no catalyst we can add or anything. It's a interesting electron tunneling mechanism. It's not collisions like we talk about with our traditional reactions. Okay, so nothing can change how quickly they go. And one area in which we take advantage of nuclear kinetics is with regards to dating old artifacts that we found, whether it's rocks or wood, or say we find a wooden figurine that looks like it might have come from Native American tribes. We want to figure out how long ago that happened. We can take advantage of nuclear decay. And so we have a problem here toward the bottom. It's kind of addressing this, where Professor Cat finds this wooden artifact, and he can look at what the percent activity of the carbon-14 is in it. And he knows the half-life for carbon-14 decay. And he wants to figure out how old the artifact is then. So let's just start with our first-order kinetics equations. Okay, so this is just our rearranged first-order equation. And the other information that they give us is the half-life of carbon-14. And then they give us information about the activity of the artifact. And so when I see that 7.9% activity of what it has compared to what it would have if it were made today. Sorry, let me re-say that. So if we were to hold a Geiger counter up to a piece of wood today and measure that, and then hold it up to our artifact, we're saying it only has about 8% of the activity that the new one does. And so what I'm going to say is that the ratio of the activities is just going to be this number, so that's 7.9%. And I think you could even put in just 7.9 for that ratio and it would work out just fine. But I'm going to go ahead and do this because that's the real ratio rather than the percentage. Okay, so we can start plugging in numbers to the equation. We can say the ln of 0.079 is equal to negative 0.693 times the time, what we're trying to solve for, divided by our half-life. And so then we can multiply over by the half-life, and then we can divide by negative 0.693. And we get that our piece of wood is 2.1 times 10 to the 5th years old. So 200,000 years old. And so the more I think about it, you'll definitely want to put in the ratio, not the percentage. So take your percentage and divide it by 100 to get that value. So now instead of looking at the carbon and wood decaying, we're going to look at the uranium from a rock decaying into lead. So we find this rock and we can see how many grams of it is made up of uranium and how many grams of it is made up of lead. And so I've drawn a little schematic to the right just to help me keep track of what's going on. And then they give us the half-life of this decay. And they want us to figure out how old the rock is. And so I like to think about what reaction's actually going on. So we have uranium-238, and it's eventually going to form lead. And then it's undergoing some decays. So it's undergoing various decays. And I don't really care what types of decays it is for this problem. I just want to remember that for every 1 uranium I start with, I'm going to make 1 lead. Okay, so that'll become important in a minute. Okay, so I guess originally this rock was all uranium. And our goal is to figure out how much uranium there was to start with. Because eventually, when we go to plug into our first order kinetics equation, we'll want to do NT over N naught, right? And so this value of NT we already know. It's what we're left over with, which is going to be the 4.09 grams. It's the denominator that we have to do some work to figure out. So we know that we have 3.22 grams of lead that was once uranium. And so we don't like to switch between elements in terms of grams, right? When we use our ratios, we use moles. It tells us this is lead 206, so that tells me I'm going to have 1 mole of lead for every 206 grams of lead. And then from that little reaction that I wrote up there, I know that for every mole of lead that I have now, it was once a mole of uranium. And then I can easily enough figure out how many grams of uranium it started as by using the molar mass. And I get that I had 3.72 grams of uranium that decayed and turned into lead. And so now I can use that number to figure out how much I initially started with, because I know that I have the 4.09 grams left, and that I lost 3.72 grams. So I must have started with that total, had 7.81 grams of uranium to begin with. So I can then get my first order kinetics equation and start start plugging in numbers for the masses and for the half-life. So I have the natural log of my 4.09 grams divided by my new total, 7.81 grams, of how much uranium there used to be back in the day. Set this equal to the 0.693 times the time that we want to figure out, divided by my half-life, which is 4.5 times 10 to the 9th years. And then I can multiply over my 4.5 times 10 to the 9th years. And I get that negative 2.91 times 10 to the 9th is equal to my negative 0.693t. So I'm going to divide over by negative 0.693. And I figure out that my rock is 4.2 billion years old. Okay, so now we're going to get into, we know nuclei are protons and neutrons held together. And we're going to talk about what is it that's holding them together. And to start understanding that, we have to first look at this topic called mass defect. So the whole idea behind mass defect is we can count the protons and neutrons in an atom. And we know how much each of those weigh. If we were to add those up all together, we should get what the overall nucleus weighs. But what it turns out is we don't exactly get that. And so let's go ahead and look at that. So we have this thorium-232. Thorium-232. I hunt for it on the periodic table, and I find that it is atomic number 90. Okay. So we can think about, let's break this up into its 90 protons. And its 142 neutrons. Oops. Okay. And so then we can go ahead and say, I know we have 90 protons. And I know that one proton weighs this 1.0072765 number. And then I can figure out how much mass all of the protons should be contributing. And I know it's annoying, but you're going to want to keep all of those sig figs when you do your calculations. And so we get that the protons are contributing a little more than 90 AMU to the overall mass of this element. And we can do the same kind of thing for the number of neutrons that it has. And we find that the neutrons are contributing a little over 143 AMU. And so to get our theoretical mass of what it should weigh, we're just going to add those two together. And we get a total mass of 233.2959044 AMU. And so if you compare that mass that we just got to the one they told us it is actually, you can see that the actual mass is less than what we just calculated. And so that's what this whole mass defect is going to be about. Our mass defect, or delta M, is going to be our ideal mass, which we calculate, minus the real mass, which they have to tell us. And so we can figure that out for this problem. We take our 233 number and subtract our 232 number. And we get a total mass defect for one nucleus that's about 1.25, etc. AMU. And so now it's like, well, where'd that mass go? Conservation of mass, right? Well, it turns out that missing mass ends up being converted to energy. And so this mass is converted to energy that's then used to hold all of the individual protons and neutrons together. So it holds the nucleus in one piece. And so what's kind of cool is that now we get to calculate that energy, and we're going to use it, or do that using the most famous equation, E equals mc squared. So, cool equation. The only annoying part about it really is that we have to be really careful with our units. Okay, because energy we think about in joules, and joules has a hidden kilogram in it, so we need our mass defect to be in kilograms. And real quickly too, I just want to say that the speed of light is like that 3 times 10 to the 8th meters per second. Okay, so let's get our mass defect into kilograms. And to do this, we're going to use one of our most favorite conversions, which is where we say in 1 gram, we have 6.022 times 10 to the 23rd AMU. And then from there we can say in 1 kilogram there's 1,000 grams. And as you might expect, we get this really teeny tiny mass that's lost for every one nucleus of this thorium. And I know the sig figs are annoying and writing out all those numbers is tedious, but if I can do it with my finger on this iPad too, you guys can do it when it comes to be exam time. So now that we have that, we can finally start getting into energy with E equals mc squared. So we can go ahead and say, and well, here, as it says on this sheet, we want to be really careful about what units they want us to end up in. So here, they want us to figure out what it's going to be in joules per nucleus. And this is what we'll get out when we just straight up plug in to E equals mc squared. So we'll have E equals our mass in kilograms. It's got to be in kilograms. Times c squared and we end up getting, so once we've plugged into E equals mc squared and we solve it out, we get this 1.88 times 10 to the negative 10 joules per nucleus. Okay, so pretty small energy. But that makes sense because we're only looking at one nucleus. Okay, just one little teeny tiny nucleus. And so we can think about writing this in different units, which would be in kilojoules per mole. And so we'll just have to do some unit conversions. This is similar to types of conversions that you probably did back in Gen Chem 1, Chem 110 land, where we take our energy for one nucleus in joules per nucleus. And then we say, well, in a mole, we're going to have Avogadro's number of nuclei. And then we'll have 1,000 joules in 1 kilogram. Or kilojoules, I'm sorry. And when we solve this, we get 1.13 times 10 to the 11th kilojoules per mole. So then you can see once you have a mole of this stuff, that's an enormous amount of energy. You don't even have like a pound of this stuff, but it can do 10 to the 11th kilojoules worth of energy, which is wild. Okay, so this third way that we look at our energy and report it is in joules per nucleon. So all we're kind of doing is, instead of saying like how many joules is it for this whole one particular nucleus, we're saying how much energy is associated with each individual neutron or proton, because nucleons are just neutrons or protons. And so we can figure out how many nucleons there are in a nucleus by just looking at the atomic number. And so, or I'm sorry, our mass number, because that gives us the sum of protons and neutrons. So the number we're going to use here is 232 nucleons. So we'll start with our original energy with the 1.87. Which is in joules per nucleus. And then we can say, well, in one of my thorium nuclei, so one nucleus, I'm going to have 232 nucleons. So how much does each one of those nucleons contribute in terms of energy to holding this whole thing together? And we end up with an even smaller energy, which makes sense because we're taking a small energy and dividing it by the number of particles. And this is going to be in joules per nucleon. And so we use these energies to keep track of what's stable and how stable something is. Because the more energy that's associated with holding it together, the more work each of these particles is doing to hold the nucleus together, the more stable it's going to be. Okay, so lots of being really careful with units here. And so with that, that's the end. You all are doing a great job, and I hope you keep up the work. And let us know if you need anything. We're here to help you. Okay, so stick with it, and you guys will make it through. Have a great day.